Today I will explain mean value theorem. Mean value theorems. Here we have two types of mean value theorems. One is Rolle's theorem, the other one is Lagrange's mean value theorem. Rolle's theorem. The proof of these theorems are not in our syllabus. Only the statements are very useful and their applications, simple applications are needed here. So coming to Rolle's theorem. F defined on the closed interval a comma b to or be a real valued function. Real valued function such that it satisfies the conditions f is continuous. F is continuous on closed interval a. F is differentiable on open interval a. And the third condition is f of a equal to f of. Then there exists at least one C that belongs to open interval a b, that lies between a b. This is belongs to a b such that there the derivative of the function is clearly 0. So by Rolle's theorem, if f is a real valued function such that f is continuous on closed interval a b and differentiable on open interval a b, and f of a equal to f of b follows, certainly there exists at least one C. At least one C means one or more such points exist that lies between a and b, where the functional derivative becomes 0. The functional derivative vanishes at those points. So this is the statement of Rolle's theorem. You can you can give the interpretation of this Rolle's theorem geometrically. So f is continuous. F is continuous means the graph of the function is continuous. There is no breaks and sudden falls in the graph of the function. And f is differentiable on AB means at each and every point in between AB, the graph of the function has derivative means that means the graph at each and every point on the graph, the tangent exists. The tangent exists at that point. Once it is differentiable means the tangent exists. Moreover, f of a equal to f of b follows. The functional values for equal at that point. Then there exists at least one C that belongs to AB such that f dash c equal to 0. F dash c equal to 0. That means the tangent at C is parallel to x-axis. One such tangent exists to the graph of the function. Once the function follows the statement of the Rolle's theorem. So geometrically it is geometrically the graph of the function f is continuous, has no breaks or sudden falls, jump or falls. That is, f is continuous in AB, on AB. The second one is at each and every point A and B, the tangents exist. Exists to the curve. At each and every point between A and B, the tangent exists to the curve. That is, F is differentiable. Differentiable over the AB. And the third one is F of A equal to F of B. The functional value at A equal to functional value at B. Then there exists a point C comma F of C on the curve where tangent is parallel to x-axis. Since such that A is less than C is less than B. Then there exists by Rolle's theorem. Then there exists a point C comma F of C on the curve where tangent is parallel to x-axis, so that C lies between A and B. Graphically, the Rolle's theorem announces geometrically you can make interpretation to the Rolle's theorem like this. Once suppose the graph of the function is like this. It is continuous, no breaks. Let us suppose x equal to A. This is A. Hence, this is F of A. This length is F of A. F of B. This is F of B. This is B and this is F of B. This is A, this is F of A. The graph of the function is continuous. No breaks and no sudden jumps or falls in the graph of the function. In such case, the graph is continuous. Once the graph is continuous in the given interval AB and it has derivative at each and every point, interior point of AB, in between AB, at each and every point the tangent exists. The tangent exists to the graph. To the curve, the tangent exists. F differentiable on AB means at each and every point between AB, the tangent exists to the curve. That is the second point. Suppose if you consider here, the tangent exists. If you consider here, the tangent exists. Like that, at each and every point, the tangent exists to the curve. And F of A equal to F of B, this length equal to this length. Once F of A equal to F of B, the function is decreasing as well increasing, or increasing as well decreasing. The graph of the function is like that. It should be decreasing to certain point and then increasing from that point, or it is increasing up to certain point and then increasing. The graph may be like this also. In case of this graph, it is increasing and then decreasing. In case of this graph, the function is decreasing as well as increasing. Okay. So, in such case, f is continuous, the graph is continuous, and at each and every point, the tangent exists to the curve, such that f of A equal to f of B. In such case, between A and B, certainly there exists one, at least one. At least one means one or more points may be exist at one point, where, what is the point on the curve here? Once this is C, this is f of C. So, C comma f of C is the point. This is the point C comma f of C, where the tangent is parallel to x axis. where the tangent is parallel to x-axis by the Rolle's theorem. Certainly such tangent exists to the curve. So the Rolle's theorem announces that once the function is continuous as well as differentiable, certainly there exists a tangent in between the given values where the tangent is parallel to x-axis. Okay, such point exists by the Rolle's theorem. Simply that is the geometrical interpretation of Rolle's theorem. Okay, the graph may be like this or like this. It may be decreasing as well as increasing, or it may be increasing as well as decreasing. At least one point, at least there exists at least one such point in between AB. Of course, the graph is supposed like this. The graph of the function is like this. Let us consider x equal to a. This is f of a, and this is f of b. X equal to b, hence f of b. This is the point b comma f of b on the curve. This is the point a comma f of a. Okay. Certainly there exists at least one point between a and b where the tangent is parallel to x-axis. Such points are here clearly. This is one such point, and this is also one such point. Let it be this is C1 and this is C2 where the tangent is parallel to x-axis. This is the point C2 comma f of C2. This is the point C1 comma f of C1. So these certainly there exists at least one such point to the graph once it is continuous as well as differentiable in the interval. In case f of a equal to f of b, then certainly there exists at least one such point where the tangent is parallel to x-axis. So that is the Rolle's theorem, the geometrical interpretation of Rolle's theorem. Okay. Coming to algebraical approach of Rolle's theorem. Algebraically, the Rolle's theorem may be announced like this. Algebraically, the Rolle's theorem may be announced like this. Taking as third point. Suppose fx is a polynomial function. Fx equal to 0 be a polynomial function. Polynomial equation. Okay. Polynomial equation means an equation which is of the form an x power n plus an minus 1 x power n minus 1 plus an minus 2 x power n minus 2 and so on a naught equal to 0. This is nth degree polynomial equation. Nth degree polynomial equation provided n is a positive integer. N being a positive integer, then you can say that this is the nth degree polynomial equation. Suppose this nth degree polynomial equation has two roots. The roots of these two real roots, namely x1 and x2. B root, x1 is one root and x2 is another root. Then let us take this one as fx equal to 0. Fx equal to 0, P polynomial equation such that x1 and x2 are two roots of that equation. Once they are the roots, then f of x1 equal to 0 and f of x2 is also 0. Both are equal. F of x1 equal to f of x2 because they are the roots. So once x1 and x2 are two roots of that equation, certainly there exists at least one root of f dash x equal to 0 in between x1 and x2 by Rolle's theorem, because the polynomial equation is continuous everywhere. That means continuous in between x1 and x2 also. And moreover, it is differentiable. The polynomial function is always differentiable everywhere. Over the set of real numbers, it is continuous as well as differentiable. Hence, it is also continuous and as well as differentiable in between x1 and x2, such that f of x1 equal to f of x2 Hence, the Rolle's theorem is applicable to polynomial functions, such polynomial functions over the interval x1 comma x2. So, by applying the Rolle's theorem to such polynomial functions, there exists certainly that belongs to the open interval x1 comma x2 such that there f dash c equal to 0. That means c is a root of f dash x equal to 0. For the derivative of fx, the derivative of fx is considered f dash x equal to 0. For this equation, c is a root. That means between any two roots of the polynomial equation, certainly a root exists to its derivative. A root exists to the derivative of that polynomial equation. Okay, that is the algebraical approach of Rolle's theorem. So, suppose fx equal to 0 be a polynomial equation such that a comma b are two roots of fx equal to 0. By Rolle's theorem, there exists at least, the word at least is more important, at least one root of f dash x equal to 0 between a and b by Rolle's theorem. Okay. By Rolle's theorem, if fx equal to 0 be the polynomial equation such that a and b are two roots of that equation, that means f of a 0, f of b 0. Certainly there exists at least one root of f dash x equal to 0 between a and b, the roots of fx equal to 0 by Rolle's theorem, because every polynomial equation is continuous and differentiable everywhere. Since fx be a polynomial equation, a polynomial function, continuous and differentiable in between the roots a and b. The polynomial function is continuous and differentiable everywhere. Hence, it is continuous and differentiable in between a b also. So, therefore, Rolle's theorem certainly applicable to such polynomial equations provided a and b are the two roots of fx equal to 0. Certainly, there exists a root of f dash x equal to 0, the equation f dash x equal to 0 in between the roots of fx equal to 0. That means fx equal to 0 roots are a and b roots. A is a root and b is a root. Then you can conclude that f dash x equal to 0 root exists between a and b, provided fx is a polynomial equation. That is that we can conclude from the Rolle's theorem. That is, we can conclude from the Rolle's theorem. This is one. At least one root exists to f dash x equal to 0. At least one root exists to f dash x equal to 1. One or more roots may be exist. For example, that means the graph of the function is like this. The graph of the function is like this. X equal to a, polynomial function is like this. X equal to a and at x equal to b, f of a is 0, f of b equal to 0. So, this is one root of the polynomial function and fx equal to y equal to fx graph. X equal to a is a root and x equal to b is another root. Between two roots, certainly there is a point where f dash is 0. The tangent is parallel to x axis at certain point. So, that is this is the root of x equal to c, that lies between a and b is root of f dash x equal to 0. This is one root of f dash x equal to 0. Okay. These are the roots of f x equal to 0. In such a way, you can apply the Rolle's theorem to the algebra in finding the roots of f dash based on fx. Similarly, I will explain the other mean value theorem, Lagrange's mean value theorem. Lagrange's mean value theorem. Lagrange's mean value theorem, LMVT. Rolle's theorem is one mean value theorem and Lagrange's mean value theorem is another mean value theorem. In this one, f a to b defined on a to b to or be a real valued function or real valued function here such that it follows the two conditions: f is continuous on AB, the closed interval AB. F is differentiable. F is differentiable on open interval AB. Then by Lagrange's mean value theorem, then there exists, of course, there exists. F is differentiable on open interval AB, then there exists at least one C that belongs to AB, an intermediate value that lies between A and B, such that one C that belongs to AB such that there the derivative f dash C is equal to fb minus fa by b minus a, provided b not equal to a, provided b not equal to a. Certainly there exists a point, at least one such point, where the derivative f dash c takes the value fb minus fa by b minus a. Okay. In case of f of b equal to f of a, it comes under Rolle's theorem. Rolle's theorem is a special case of Lagrange's mean value theorem. Once fb equal to fa for a not equal to b, fb equal to fa for a not equal to b, then clearly f dash c equal to 0, which comes under Rolle's theorem. So Rolle's theorem is a special case of Lagrange's mean value theorem itself. Okay. So certainly there exists at least one C that lies between the open interval AB such that there the derivative takes the value fb minus fa by b minus a itself. This is Lagrange's mean value theorem. Okay. Geometrically, the Lagrange's mean value theorem, once the graph of the function is continuous and each and every point in the domain of the function, the derivative exists to the function means the tangent exists at each and every point of the graph that lies between a and b. Once the function, graph of the function follows the two conditions, continuity and differentiability, then at least at one point in between a, b, the derivative always f dash c, that means the tangent is parallel to the chord that joins the points x equal to a and x equal to b. That means once you take like this, let it be this is x equal to a and this is x equal to b. Of course, this one is x equal to b. This is f of b, this is f of a. This length is f of a, this length is f of b. Hence, this is the point on the graph where a comma f of a lies. This is the point on the graph b comma f of b. Okay. fb minus fa by b minus a. Difference of y coordinates by difference of x coordinates gives us the slope of joining of these 2 points. So the chord AB, let it be this is the A and this is the B. The chord AB slope is given by FB minus FA by B minus A. The chord AB. Slope is given by FB minus FA by B minus A. This chord is always parallel to F dash G, a tangent, which was drawn at an interior point or intermediate point in between AB, such that there the tangent is always parallel to this chord. Certainly there exists one such tangent, which is parallel to the joining of these 2 points. The Lagrange's mean value theorem announces like that. This is the geometrical interpretation of Lagrange's mean value theorem. That means once the graph is continuous in AB and differentiable means the tangent exists at each and every point in between AB. Certainly there exists one point where the tangent is parallel to the chord joining the end points of the interval here. These are the end points of the interval. This is the chord AB. AB is parallel to this one. At this point, this is the point C comma F of C. At this point, F dash C is clearly FB minus FA. This is equal to B minus A. The slope of this tangent is parallel. Since the slopes are equal, these two are parallel. You can say geometrically in such a way, certainly a parallel tangent exists to the curve 2AB. Okay, that is the geometrical interpretation of Lagrange's mean value theorem. So geometrically the join of A comma F of A, B comma F of B on the continuous curve Fx in AB. The join of A, F of A, B comma F of B on the continuous curve Fx equal to Fx in AB is a chord. That join is a chord which is parallel to a tangent drawn at C comma F of C, where C belongs to A. Such tangent exists by Lagrange's mean value theorem. Once F is continuous and it is differentiable in the sense at each and every point on the curve the tangent exists. Once the tangent exists, out of all such tangents, one tangent is certainly parallel to the chord that joins AB. So the join of A comma F of A, B F of B on the continuous curve Fx curve y equal to Fx, of course, in AB is a chord which is parallel to a tangent drawn at C comma F of C, where C belongs to AB. Such tangent exists. By Lagrange's mean value theorem. Such tangent exists by Lagrange's mean value theorem. Okay, that is the geometrical approach of the Lagrange's mean value theorem. So certainly a tangent exists to the curve so that it is parallel to the chord that joins the end points of the given interval, in which the function is continuous. That means the graph is continuous as well as differentiable. That means at each and every point the tangent exists. This is Lagrange's mean value theorem. Rolle's theorem is a special case of Lagrange's mean value theorem. once Fb equal to Fa, where A not equal to B, then the Lagrange's mean value theorem reduces to Rolle's theorem. That is one important point. I will explain through an example here. Let us take one simple problem. Verify Rolle's theorem for fx equal to sine 2x in the interval 0, pi by 2. Verify Rolle's theorem for the function fx equal to sine 2x in the interval 0, pi by 2. Verification of the Rolle's theorem. Verification means a check whether the function follows the conditions of Rolle's theorem and whether it consists of at least one value that lies between the given interval 0 to pi by 2, where the first derivative becomes 0. That is important here. So, this is the verification method. Given the function is here, given fx equal to sine 2x for all x that belongs to 0 to pi by 2. X lies within the closed interval 0, pi by 2. Now, first one. Since sine function is continuous, sine graph is always continuous in the given interval. So, in 0 to pi by 2, fx equal to sine 2x is continuous. You can announce, since the sine graph is continuous over the interval, since sine graph is continuous on R itself, since the sine graph is continuous on R itself, the given function fx equal to sine 2x is continuous in this subinterval. This is the subinterval of R, a particular values of R, real values. So, on set of real numbers it is continuous since the graph is continuous. In the small interval, subinterval, it is also continuous. And then second one, f dash x is here. For sine 2x, the derivative is 2 cos 2x. F dash x equal to fx equal to sine 2x, fx equal to sine 2x, f dash x equal to 2 cos 2x. It is the derivative of the function, which exists, the derivative exists for all x that belongs to, of course, 0 to pi by 2. In the closed interval itself, it is exists for every value x that lies between 0 and pi by 2, whatever may be the value that you consider in the first quadrant. F dash x equal to f dash x takes finite value, which exists means it takes a finite value. Okay. At x equal to 0, it takes 2. At x equal to pi by 2, it takes cos pi minus 2. It varies between minus 2 and plus 2. So, it takes a finite values whenever x lies between 0 and pi by 2. So, hence the function f has f is differentiable. The given function f is differentiable on the open interval 0 to pi by 2. You can conclude like that. Since it is differentiable in closed interval itself, it is clearly differentiable on the open interval. The first condition of Rolle's theorem valid and the second condition of Rolle's theorem valid for the given function. Coming to third point of the Rolle's theorem, check whether f of a equal to f of b. Here a equal to 0, b equal to pi by 2. So, here f of a, let us consider f of 0, f of a value, that is sine 0, which is 0, and f of b, that means f of pi by 2, that is sine 2 pi by 2, 2 into pi by 2, sine pi is 0. So therefore, f of 0 equal to f of pi by 2 follows. The third condition of Rolle's theorem also follows. The given function sine 2x function continuous over this interval and differentiable over open interval 0 to pi by 2. The first two conditions of Rolle's theorem valid, and moreover the third condition also valid, because f of 0 is 0, f of pi by 2 is also 0. So the third condition also follows. Hence by Rolle's theorem is applicable. Rolle's theorem. There exists at least one C that belongs to open interval 0 comma pi by 2 such that f dash C is 0. There the functional derivative vanishes. F dash C equal to 0. What is f dash C? Clearly f dash C is, that is 2 cos 2C is 0. 2 cos 2C is equal to 0. So therefore cos 2C is 0. Therefore 2C takes the value pi by 2. Therefore C takes the value pi by 4, which belongs to 0 comma pi by 2. Clearly the point C lies between 0 and pi by 2, because it is pi by 4. Once 0 and pi by 2 is here, pi by 4 is C, this is A, this is B. There the first derivative 0. At this point f dash C is 0 clearly. So hence certainly there exists a point in the name of pi by 4, intermediate value of 0 pi by 2, where the first derivative of the function becomes 0 by Rolle's theorem. Hence the Rolle's theorem is verified. Rolle's theorem, because it lies in the interval 0 to pi by 2 clearly. Rolle's theorem is verified. Verification of Rolle's theorem is completed. Hence Rolle's theorem is verified. Once the obtained C does not lies between A, B, the values, the Rolle's theorem is not applicable. Okay, the Rolle's theorem is not applicable. This is the way of verification of the Rolle's theorem for the given functions. Okay. Next one. Next another problem. Verify Rolle's theorem. For fx equal to mod x in minus 2 comma 2. Verify Rolle's theorem for the function fx equal to mod x in the interval minus 2 comma 2. Okay. Given fx equal to mod x, that implies fx equal to, for of course minus 2 is less than or equal to x is less than or equal to 2. That implies fx equal to x for x being positive. X being positive means 0 is less than, x is less than or equal to 2. And minus x, once this value is negative, it takes the value, fx takes the value minus x. Ultimately we are getting positive value. And at 0, if x equal to 0. By definition of the mod x function, mod x takes the value x whenever x is positive, mod x takes the value minus x whenever x is negative, and mod x equal to 0 for x equal to 0. This is the definition of the mod x. By definition of the mod x, you can take once x is positive, that means x lies between 0 and 2, it takes x. Whenever x lies is negative, that means minus 2 is less than or equal to x is less than 0. It takes mod x is minus x and 0 for x equal to 0. Once you draw the graph of this function, it is clear that for x being positive 1, 2, whenever x lies between 0 and 2, the graph is y equal to x. Y equal to x means like this. This is the line fx equal to x. Both x and y takes the same values, of course. Hence, it is a line y equal to x line. In case of x lies between minus 2 and 0, the graph is minus x. In such case, the graph is like this. The graph is like this. Okay? The graph is like this. Fx equal to minus x. For x equal to 0, this is 0. This is the 0, 0 also included in the graph. 0, 0 also included in the graph. So the graph is in the V shape. It never crosses x-axis. It never come down to the x-axis because modulus of x, since modulus of x is always greater than or equal to 0 for all x. Okay. Modulus of x is either positive or 0. So hence it passes through, graph passes through 0 and it is above the x-axis. It cannot come down to the x-axis. So this is the graph of the function. It is in the V shape. Okay. Once you consider f of 2 means this length f of 2. Similarly, f of minus 2, this length. Both f of 2 and f of minus 2 are same because modulus of 2 equal to modulus of minus 2 equal to 2 itself. Mod 2 is 2, mod minus 2 is 2. So hence this value is 2, this length is 2. So f of a equal to f of b follows. And there is no breaks in the graph of the function because origin is also included in the graph. So here f of minus 2 is modulus of minus 2 equal to 2 and f of 2 equal to mod 2 equal to 2. Therefore, f of minus 2 equal to f of 2 follows. The third condition of Rolle's theorem follows. Similarly, from the graph of the function here, this is y-axis. From the graph of the function, from the graph of function, f is continuous on minus 2 to 2, since there is no break in the graph in the interval minus 2 to 2. The f is continuous. From the graph of the function, one should conclude that f is continuous. There is no break in the graph. And the second one is f has a corner. The graph has a corner at 0. Since it has a sharp corner, conical corner in the graph, there the derivative does not exist. That is one important point. F has no derivative at x equal to 0, since the graph has a sharp corner. A sharp corner. Since the graph has a sharp corner at 0, 0. So f has no derivative. It's not differentiable. That is, f is not differentiable at x equal to 0. Since f dash of 0 plus the derivative at 0 plus, right to that of 0. Right to that of 0, the derivative is 1, because right to that of 0, the derivative of x is 1, hence 1. And f dash of 0 minus, that means left to the dot of 0, the derivative is minus 1. Derivative is minus 1 here. Okay. So therefore, these two are not equal. Right derivative is different from left derivative. Hence, f is not differentiable. Okay. Graphically, you can say like this. If the graph of the function has a sharp corner or conical corner in the given interval, then you can say that at that particular point, at that particular sharp corner, the function is not differentiable, because the right derivative is different from left derivative. The right derivative is here clearly 1. The left derivative of the function is minus 1, because the derivative gives a slope. Slope of this line is for positive values 1. Slope of this line is for negative values of x. The slope of the line is minus 1. So the slopes are not equal. Hence, the right derivative is different from left derivative. F is not differentiable. Out of 3 conditions of Rolle's theorem, 2 followed. Third one, f of a equal to f of b follows here, and f is continuous but not differentiable at 0. So since it is not differentiable, the Rolle's theorem is not applicable to this problem in the interval minus 2 comma 2. So the second condition of Rolle's theorem does not follows here. So hence, fx equal to mod x, for fx equal to mod x, Rolle's theorem is not applicable. Theorem is not applicable. In the interval minus 2 comma 2. This is the way of verification of the Rolle's theorem for the given function. The Rolle's theorem may not applicable to this function. It is applicable only in case of it is continuous as well as differentiable and f of a equal to f of b. All the 3 conditions follows. Only it is applicable. Moreover, at least one c, in such case one c certainly lies between that values where the first derivative becomes 0. That is the verification of the Rolle's theorem for a function. So here the Rolle's theorem is not applicable to the given function. Next problem. Verify Rolle's theorem. Verify Rolle's theorem for fx equal to x square minus 5x plus 6 in the interval 2 comma. Verify Rolle's theorem for fx equal to x square minus 5x plus 6 in 2 comma 3. Okay. Fx equal to x square minus 5x plus 6. A polynomial function of degree 2 function. Hence it is continuous and differentiable. every polynomial function is continuous and differentiable over the set of all reals. Hence, it is continuous and differentiable on 2, 3 itself. In between 2 and 3 also, it is continuous and differentiable because it is everywhere continuous and differentiable. Moreover, f of 2 at one end, left end value of x, the interval, the functional value f of 2 is 2 square minus 5 into 2 plus 6, 4 minus 10 plus 6 is 0, and f of 3, 3 square minus 5 into 3 plus 6, 9 minus 15 plus 6 is 0. Therefore, f of 2 equal to f of 3 follows. The third condition follows. First two conditions follows and third condition follow in this case. Hence, by Rolle's theorem is applicable. So, by Rolle's theorem, there exists at least one C that belongs to 2, 3, that lies between 2 and 3, such that f dash C equal to 0. F dash C means 2x minus 5 at C, at x equal to C is 0. That is 2C minus 5 equal to 0. C equal to 5 by 2, 2.5. It belongs to 2, 3 clearly. 2.5 lies between 2 and 3 itself. C must lies between 2 and 3. That is verified. So, therefore, Rolle's theorem is verified. Verified for this function in the given interval. Verification means you have to find such C. That C must lies between, check whether the C lies between the given interval or not. Clearly, it lies in the given interval, open interval 2, 3. Hence, the Rolle's theorem is applicable to the quadratic x square minus 5x plus 6 in the interval 2, 3. Graphically, once you announces this problem graphically, once you draw the graph of this function, taking x equal to 0, we get y equal to 6. The graph passes through 0, 6. Moreover, taking fx equal to 0, x takes the value 2 and 3. X takes the value 2, 0, the graph passes through 2, 0 and 3, 0, because f of 2 is 0 and f of 3 is 0, the graph passes through 2, 3 also. So, the moreover, x square coefficient is positive. Once you join these three, you can draw the graph of the function. This is f(x) equal to x square minus 5x plus 6. This is the graph of the function. Certainly at 2.5, there is one point that lies between 2 and 3, where the tangent is parallel to x-axis as per geometrical interpretation of the Rolle's theorem. It is clear that the tangent drawn at this point 2.5, f of 2.5, this point, taking x equal to 5 by 2 in this one, we get f of 2.5. At this point, the tangent is clearly parallel to x-axis. So, in such a way, you can express the Rolle's theorem geometrically. This problem, you can develop that problem geometrically and express the Rolle's theorem. Okay. I will on derivatives, coming to derivatives and other values. Okay. I will give one more problem. Find C. Find C by Lagrange's mean value theorem for the function f(x) equal to x square in the interval a comma b. Find C by Lagrange's mean value theorem for the function f(x) equal to x square in the interval a comma b. The curve f(x) equal to x square, the graph of the function. Curve is, the given function is f(x) equal to x square, defined for a less than or equal to x less than or equal to b. X lies between a and b. Since it is a polynomial, since f is a polynomial function, hence f is continuous on the given interval and it is also derivable. F is derivable. Since f dash x is 2x exists a finite value in a b. Okay. F is continuous on closed interval a b and f is derivable on open interval a b. Since f dash x equal to 2x takes a finite value whenever x lies between a and b. Both the conditions of Lagrange's mean value theorem is valid in case of x square. So by Lagrange's mean value theorem, by LMVT, there exists at least one C that belongs to open interval a b such that f dash c equal to f of b minus f of a by b minus a. F dash c equal to f of b minus f of a by b minus a. That is f dash c. F dash c means 2c equal to f of b, b square, f of a square by b minus a. Therefore, 2c takes the value b plus a because b square minus a square may be factorized as b minus a into b plus a. B minus a cancel here. So, 2c takes the value b plus a. So, c takes the value a plus b by 2. A plus b by 2 is the mean of a b. Once a and b are considered on the real line, a plus b by 2 is midpoint of a b. This is c here. So, the c is certainly, it belongs to the open interval a b. Hence, the Lagrange's mean value theorem is valid and certainly there exists one such intermediate value that lies between a and b as a plus b by 2 for the function f(x) equal to x square. F(x) equal to x square graphically, it gives us y equal to x square graph. Y equal to x square is symmetric about positive y axis. Y equal to x square, either x is positive or negative, y is positive itself. So, the graph is a parabola. A parabola passes through origin. Okay. The parabola. The graph is a parabola. It is not a corner. It is a free curve at origin. You can check it. Y equal to x square. A free curve. It is not a sharp corner at origin. Y equal to x square is graph of a parabola, which is continuous, as well as tangent exists at each and every point. Hence, it is continuous as well as tangent exists. Let us take the point x equal to a. That means this is the point a comma f of a. Another point, take b. This is the point b comma f of b. Once you join this, you get a chord. That chord is certainly parallel to the tangent drawn at a plus b by 2. Drawn at the point a plus b by 2, f of a plus b by 2. So, such tangent can be drawn to the curve by Lagrange's mean value theorem. The tangent is always parallel to this chord. The chord is parallel to such tangent. That is the geometrical procedure of Lagrange's mean value theorem, application of Lagrange's mean value geometrically. Next, Cauchy's mean value theorem. This is one more mean value theorem. Cauchy's mean value theorem. This is one more mean value theorem of derivatives. Okay. Once f a b and g is also defined from a b to r, be given real valued functions such that f comma g are continuous on AB. Continuous on AB such that g dash x is not equal to 0 and f of x is not equal to 0. G of a equal to g of b. F and g are continuous in the closed interval AB such that f dash x, its derivative not equal to 0, and g of a is not equal to g of b, and are differentiable on the interval AB. Then there exists at least one C that belongs to the open interval AB such that f dash c by g dash c equal to f of b minus f of a by g of b minus g of a. Okay. F and g are continuous functions over the closed interval AB, and they are differentiable on the open interval AB. And g dash x is not equal to 0. The derivative is not 0 in between AB. And g of a not equal to g of b, g of a not equal to g of b. Then certainly in such case there exists at least one c. There exists at least one c, one intermediate value in between a b. There f dash c by g dash c is always equal to f b minus f a by g b minus g a. Just generalization of the Lagrange's mean value theorem to two functions. F dash c by g dash c equal to f b minus f a by g b minus g a. It announces the Cauchy's mean value theorem, the generalized mean value theorem generalized procedure of Lagrange's mean value theorem. Okay, this is an important mean value theorem. This is one important mean value theorem. In 2014, I thought that based on this one question is set on this problem. One question is set on this problem. Okay. In the next class, I will explain the problems related to Lagrange's mean value theorem, Rolle's theorem, and this Cauchy mean value theorem. We will take one more hour to deal the important problems covered in mains, JEE mains. Okay.